Right, so we're ready to continue the lecture with Francesca.
Thank you, John. So we were here. We are almost there describing the Hilbert space because we have described the operator algebra. So I told you, so here I am just putting an L here. Now you know who is L. There are the generators of SU2 transformations. They are associated with the tetrads and so on. And they are the building block to construct operators that represent physical quantities, such as area and volume and angles and so on. So you can write the algebra of these operators for each of these different observables. So the question is now, okay, we have this Hilbert space, and I have defined it in a very general way, talking about states of the theory that are functions of SU2. And the next, so we have defined these operators, and now I want to define a particular base in the theory using these generic states written in terms of group elements. And I wanted to define in this Hilbert space a particular decomposition of the Hilbert space so that my states will be written in a basis that diagonalize the intestine physical quantities, namely the area and the volume. And this is what the spin network states do for you. The spin network states that we'll define in a second are an overcomplete basis in my Hilbert space of the theory. And how do I obtain them? Well, as I said, I just take my Hilbert space. At this moment, we just take the Hilbert space defined on my links, and I can show that using Peter-Weyl theorem, I can decompose this Hilbert space as a tensor product of Hilbert spaces defined for each J representations, any spin associated with the representations of SU2, and the full Hilbert space is given by the product of these representations, and then the full Hilbert space is given by summing over all the spins. But this is just one step towards the Hilbert space that we had before, because you should remember the fact that the full Hilbert space had implemented a gauge symmetry at each node. So I had to impose, take a quotient of such that each node was gauge invariant. So in this Hilbert space, with this tensor decomposition of my Hilbert space, I needed to select a particular subspace that is the one that corresponds to the gauge invariant sector. So this sector, invariant under SU2 transformation, is called intertwiner space. So intertwiners in representations theory are in gauge theory, in the theory of in group theory, are those objects such that you can combine different representations in a gauge invariant manner. So I have this intertwiner space, and in this intertwiner space, finally, I can define my spin network basis. So it's this state that you see here that is characterized by three quantities. So for each state, I have to define for which auxiliary graph I'm using. Okay, this is my gamma. Then I have to tell the representations that are of SU2 that are associated with the links, and then I have to select the particular intertwiner that I am picking up. So in 3 dimensions, this intertwiner, in 1 dimension less, the intertwiner is completely defined. In this case, you have to tell which one. So these are the quantum numbers, the spins and the intertwiners that label my states. And so the full state that we defined before is this state that now is obtained by a direct sum over the J's, and then the product over the Hilbert spaces for each node. And this is a very appealing way to write things, because it's like you can define things locally. We will somehow identify each node with a region of space-time, or if you want, with the space-time quanta. And now my Hilbert space is given by the tensor product of all these locations, let's say, all this quantum space. So now this is the question that I was asked before. What are these states about? Okay, now I can tell you this. Now we are writing the states of the theory in this particular base, such that I can diagonalize area and volume. So these are eigenstates of area and volume. Of course, we said before, the eigenvalues associated with these states are discrete. This is what we have seen before. So this is finally a full quantum geometry, a full description of a quantum geometry where we said that because we had the Penrose spin geometry theorems, we can think of these objects in a very geometrical manner, but these objects are not just a rigid geometry. So you don't have you can picture polyhedra, but these polyhedra are not classical objects. They are fuzzy because the geometry is such that the operators do not commute, and of course, even more, the full definition of this theory is such that a generic state in this theory is not just a single spin network. So spin network, now I'm using the word spin network to indicate this class of state. So it's not just one state with a given decorations with this quantum number, but a generic state of the theory is a superposition of these states. Okay. So even more, I can connect this. So we can make a first link between these objects that is defined completely at the quantum level, and just say, okay, I have a Hilbert space, I have observables, and this is my quantum geometry. I can make the first connection with a classical geometry. So these are quantum state of my theory, and I can try to describe semi-classical states. So semi-classical states means that I have to look for those states that have minimal spread. In general, quantum states are can have. We say that they are fuzzy. But we can select a special class of states that are just the analog in the case of states defined with group variables, but they are just the analog of coherent states that you know from quantum mechanics 101. So in quantum mechanics, you have seen how to write states that are peaked with a minimal spread in a certain position and in a certain momentum. So you try to define them so that you minimize the spread in those two components, in these two variables. And you wanted to do the same here, where your position and your momentum are basically area and curvature. So actually, for the moment, we wanted to define intrinsic coherent states. So for the moment, we just think of this polyhedra, and each of them has spread in the area, and I wanted to see when the area is maximally peak. So it is well known in quantum mechanics that so if you have an angular, if you consider the angular momentum, for instance, that is like here, labeled by the spins. So you can have different states for spin equal 1/2, 1, and so on. But then, in the moment in which the spin is maximum, then the spread is minimized. So this is what I am representing here. So I am considering. So in this class of states. So for the moment, I just consider SU2 states. So this would be my spin and my magnetic number. So I take the magnetic number to be the maximum one, so equal to the spin J. And this is the way in which I maximize coherence. So, the question that was there.
Yeah, I think you've already answered that, but my question was, if the area operator has discrete eigenvalues in this basis, then what does spread mean? But I think... Well,
the eigenvalues, so it's like in the case of the angular momentum. Of course, you have discrete eigenvalues, but so the generic states is given by, as we say, superposition of states, and the value, so you can compute the spread, and the spread could be as large, could be very large if the states are very quantum. And the more you go toward classical values, the more you have your states that are peaked on a given value. And so this is what you want to do here. And so when we talk about the spin and the angular momentum, we are thinking in particular, so you consider a particular, the Casimir of the angular momentum, like your Jz in the Z direction. So I am minimizing my spread in that particular direction, okay? The problem is that I want to do this for every possible direction. So this amounts just to rotate my object. So I can add here an H at the nodes. So that means that I am rotating my system. So in this way, I can cover all possible directions. And the result is that I have... So like, I can just change the direction here, and the results are coherent states. Notice the fact that I want these coherent states to be such that the SU2 symmetry is preserved. So I take a group averaging here, and I represent the fact that I am considering all possible directions here. So this is for one operator L. I wanted to do this for polyhedra in which I have many faces. So this means that I have, so if I have, for instance, the simplest possible convex polyhedra that is a tetrahedron, I will have 4 faces. And I need to take the tensor product over all of them. So this define a notion of geometry in which the spread is minimal, and so in particular, it's I am minimize the spread in the curvature. If I wanted to define states such that I minimize both area and the spread in both area and curvature, then I will do I need to go through a few more steps. So the definition of coherent states can be done in different manners. There are different versions in the literature, and it depends a bit on the physical problem you want to address. Yes?
Thank you. So I have a question regarding like this minimal spread. I am assuming like if you're like looking at the coherent states, it's something like getting into the classical, no? Like closer to the classical. But then my question was like, if you are having a minimal spread in J, due to the uncertainty principle, wouldn't you have like something maximal spread?
Yes, of course, the conjugate variable.
Okay, what's sorry, the conjugate variable?
So if you maximize, so in this case, these are intrinsic coherent states in which I minimize the spread in the curvature, but the areas are fuzzy, are maximally spread. Or I can, so this is one possible definition of the coherent states. So then you can say, maybe I want to consider a situation in which I take a compromise. So I try to minimize at the same time the spread in the areas and the spread in the curvature, and these are called extrinsic coherent states. Okay. So in the easiest thing you can do is to pick up one aspect of your geometry and simply pick the states with respect to that particular quantity. This is a choice. It depends, again, it depends on the kind of problem you're interested in. There are some problems in which, rather than doing this choice, you can choose to minimize the spread in both. So it will be less picked than in this case on one variable, but you will have a good compromise so that you have a classical geometry in this other sense. But in both cases, the point is that think about so I would like to anticipate a bit what will come next, because these states will be the one with which, for instance, we will compute transition amplitudes. So, and I was saying, really, the idea is that let's try to do things operationally. So I go and I measure a certain geometry, or let's say that I have a problem in mind and I know what is the classical configuration that I wanted to describe. So when I construct a quantum state that is picked on that particular geometry. That geometry could be the one of Minkowski, for instance, if I wanted to do the propagation of a graviton, or could be a Schwarzschild geometry in the case of black holes. So it could be a homogeneous and isotropic geometry. So the nice thing of the coherent states is that they have an interpretation in terms of a classical geometry. So when we wanted to describe that particular geometry, we know how to construct them. And then, but this again is not a classical geometry in the sense that it's fuzzy, it comes with all the fluctuations of a quantum geometry and so on. Good.
Thank you.
Good, okay. But now, so this is all kinematical, okay? Oh, okay.
Yeah, I have. Oh, thank you. I have two questions for the previous slide.
Yep.
Just quick questions. In the expression you had for the that one, this H triangle,
Yeah.
and then this state. What does the triangle specifically mean?
So it's the action of the group on these SU2 states. So the action of the group means that I am rotating them in any possible direction. And then another, sounds good?
Yeah.
Okay.
And then the other one was on the left side of that equality, you have the your state indexed by I, but then on the right side, it seems like we have a tensor product over all the i's. So
yeah. So the point is that yes, but why it's not disappearing? So you are summing over all of them. So we say that depending on the geometry you are describing, so it's not a sum, it's a tensor product. So you need all the pieces. You need one. So if you want on the left hand side, you are taking one of these for each face of your polyhedra, and so this in this part. So you have this tensor product. But sorry, I'm missing why you think it should disappear.
On the left-hand side, JI doesn't mean for one specific I.
Yeah, so it's a sum. So sum, it's considering all of them.
okay, thank you.
Yeah, so, sorry for the confusion. So it's just a matter of notation. The point is that you're considering a full thing. So try to imagine concretely you have all these, for instance, a polyhedra and so on. Okay. More questions on this part? Because I want to go to the actual dynamics. So everything that I said so far is to define the Hilbert space, to define the observables, and now the true main job is to define this thing here. And what we said before was that so this theory that I'm telling you about is called covariant. And in my answer before, I said, okay, it's because with respect to what you would do, for instance, following other procedure, for instance, in the canonical theory, you want to stay fully covariant as much as possible. And in particular, you want to not gauge fix from the beginning the object you work with, okay? So the states, so let me describe what is gonna happen. Here we have defined states, and the states that are functions of these H variables, and then we have seen that I can write them in the spin network basis. But these states were states of space. And what I want to do now is to use them as an ingredient in computing processes. So when we do scattering amplitudes in quantum field theory, for instance, you have a given state that could be a state with in the Fock space, like a state with one particle, two particles, and so on. And then you have some vertex that codes that there is an interaction. And then after this interaction, you have a final state with maybe a different number of particles. So now my states, my in and out states are states of the geometry. I was telling you, imagine you make a measurement of your quantum geometry, then you make another measurement of the quantum geometry at the later time. These two geometries may be different, and I want to know the probability given my initial state to find the final one. But so these states are three-dimensional space state, and what I want to describe is an interaction that is somehow how these states evolve in time, so that somehow this span a four-dimensional Lorentzian space-time. So the states I described before will now live on the boundary of a four-dimensional Lorentzian region. And somehow I wanted to make a description of local physics. Local, again, in the sense of quantum mechanics, because I have processes, interactions, and so on. But the magic here is that my process, my interactions in quantum mechanics, in the case of quantum general relativity, is space-time itself. So space-time is how these states evolve. So this is what we want to do. What we want to do is to make sense of what we said at the beginning. Make sense of a path integral, or the discrete analog of a path integral, in which we sum over possible histories of geometry from an initial to a final state. And I told you that the key point here is that we want to be fully covariant. So before, I gauge fixed my theory because I picked up a particular foliation, and then I was describing states that were living in this space. But now, let's imagine that we construct the same Hilbert space as we did before, and we construct states of this Hilbert space, but instead of having functions that are valued in SU2, we have functions that are valued in the Lorentz group. And as we did before, instead of working with SO3, we worked with a double covering that is SU2. And here, the double covering of the Lorentz group is called SL2C. Okay? So I will talk about SL2C all the time. So this is a way in which we can fully implement the fact that my amplitudes are Lorentz invariant. And so what follows here is that I can still work with the graphs. So these graphs are still living on the boundary of my region, okay? And for the moment, I define on these graph states, so I define these graph states as being in a Hilbert space, but this time the Hilbert space, it's exactly the same as before, but with SL2C group variables, with SL2C group elements. So this is what I'm saying here. So my states psi are functions of SL2C group elements that I call capital H, one for each link. So what I'm doing is to throw away the gauge fixing that I did before. But notice that if I do so, I have a Hilbert space that is much bigger than the one that I was using before, okay? So here on each link, I have a group element, as I said, that I can think as an holonomy of the connection, of the spin connection. And instead, before, I had a state, I had a space that was defined in SU2. So this new space is much bigger, and I have to find how the old space is embedded in this new one. So I need to find a subspace in my new Hilbert space that is isomorphic to the one I had before. Any question? So the core of the story is that we need to make sense of defining how to constrain this new Hilbert space so that it fits with the one that we had before. And to do this, it's important that we make a step back, and I remind you some of the things that you have seen this morning with Christina, just briefly. So Christina this morning was introducing the tetrads that are one form, and then the spin connection that, as we said, is in SL2C. And then you can write an action for general relativity, but you need to write it properly. That means writing it with this term that's called the Holtz term. So I have this action, and you can see this action is written in terms of the tetrads and the spin connection. And in fact, I have the object here that is the F, that is my stress tensor, and I can ask in particular, so starting from the spin connection that is my SL2C object, I can ask what is the conjugate variable to the spin connection. And if you look at the action, you discover that the conjugate momentum is this capital J written in this particular way, where you have the tetrads, and you have two terms that are exactly the same, but for one you take the Hodge dual, and you have a proportionality constant between these two terms that is given by 1 over gamma, where gamma is the notorious Barbero-Mirzi parameter. So notice that in this slide, everything that I am presenting is just the classical theory. Usually, we don't put the Holtz term in the classical expression of the action. Why? Because this is a topological term. That means that when you compute the equation of motions for general relativity, this term doesn't play any role, so you forget about it. But this is a term that is completely it has the right to be there, and it plays an enormous role, as we will see in the quantum theory. This is very similar to what happens in QCD. So in QCD, if any of you is familiar with it, you have a topological term in which you have a proportionality parameter that is called theta. And here, the gamma is very similar to the theta QCD. So, my Barbero-Mirzi parameter is my theta LQG, if you want, okay? So we are arrived at this point in which we have defined what are the conjugate variables that I am considering, what is the symplectic structure of this theory, and I'm saying I am picking up this shape, this particular form of the conjugate momentum. Now, notice the fact that in general, I can have a much wider choice of possible conjugate momenta to the spin connection. So here what I'm doing is to pick up, to constrain the space of possible, so somehow I am restricting my phase space, making this particular choice. What's happening here is that, again, I'm trying to make a reference for those of you who may be familiar with this. Here I have an expression for the action that is written in terms of the tetrads and F that is a two-form. But also my conjugate momentum is here a two-form. So I have a way to write the theory, to write a generic theory here that is called BF. So I have B and F, and so that you can see as conjugate one another. And what I'm telling you is that this B2 form cannot be anything. It has to be with this particular shape given by the J. So BF theory, for those of you who knows it, is a theory that is topological, so there are no propagating degrees of freedom. Instead, the fact that I am restricting the choice of B to take this particular form, so the fact that I am making this choice of the conjugate momentum to the spin connection implies that I am actually restricting my theory to the right numbers of degrees of freedom. So I'm restricting the degrees of freedom of my theory. How many degrees of freedom? In fact, I have just to count the components of this object. It's a two-form. I have two antisymmetric Lorentz indices, so they are 6, and so it's 6 by 6, so that means that I have 36 components. And remember that my goal was to connect this with the theory that I have defined before, but the theory that I have defined before was just given in terms of the tetrads. And the tetrads are one form in which I have 4 by 4 indices, that means 16 components. So the fact that J is defined just in terms of the tetrads implies the fact that there should be some constraints that is playing a role here. And in the end, we are interested in the physics, so we need to interpret what's going on, what is the meaning on constraining these objects. And it's convenient to express this in terms of a particular choice of gauge. So let me add one more thing, because here I said that my J has 2 Lorentz indices. So this is very similar to the F mu that you have, for instance, in Maxwell theory, in which you have an electric and a magnetic field. So what we want to do is to re-express the constraints that we are imposing so that we have the analog of my electric and magnetic field, okay? So I can interpret these 2 components in a similar way as I do for electromagnetism. And the magic is that one can show that J takes the form that you have seen before with this particular writing, E, with G, and so on, if and only if there exists a Lorentz frame. That means if there exists a choice of gauge in which the analog of the electric and magnetic fields take this particular shape that you see here. So the analog of the electric and magnetic fields are the L that I can call the electric component, in which you see that I have only spatial indices. And then another component that is K, let's call it the magnetic part, in which I mix the indices, the spatial indices indicated with I, with the time indices that is, of course, indicated with 0. So now I am ready to interpret these two objects in the quantum theory, because J is the generators of SL2C transformation, the generator of Lorentz transformation. But the Lorentz group, we said, can be decomposed into boosts and rotations. So now we can see that the L are associated with the rotations and the K are associated with the boost. And the form of J constrains the boost and the rotations to be proportional to one another through this parameter, this proportionality parameter that is gamma. And I think this is magical, because this is basically what defines the quantum dynamics, imposing these constraints that I elevate to a constraint among quantum operators, so between the operator that represents the boost and the operator that represents the rotation, is basically what tells the dynamics, what is the dynamics of the theory. Now, let me go back to my spin networks in SO2. So we said that we had the Hilbert space in which I have SL2C representations, and I wanted to do the same decomposition of the Hilbert space as I did at the beginning of this lecture for the spin network Hilbert space, okay? So I have to go a bit into the technology of representations of the Lorentz group. And notice here that we are using unitary infinite dimensional irreducible representations of the Lorentz group. That is a bit different than what you could have seen in other situations. So let's see how it works. So these representations are labeled by two numbers, as opposed to the fact that my SU2 representations are labeled just by the spin, and then I have associated the magnetic number. But basically, when I write the representation, it's just one thing. In the case of SL2C representations, I have to consider now two numbers. One is called K, and is a half integer, as before the spin. And then I have another number that I call nu, and you can see this is a real number. So now I write my states in a way in which, so these two numbers are labeling my SL2C states, but I can decompose these states in a base such that this is labeled by SU2 representations, labeled by the spin J. So this is what I am doing in this second line. So notice that this space decomposes into SU2 representations such that they appear each only once, and you have a sum that goes from k, that is like the minimal j, to infinity, because we said that they are infinite dimensional. Okay, so next thing. What are the Casimirs of SL2C? I have not one, but two Casimirs. These Casimirs are given by k squared minus L squared and by k times L, so that that are related to the quantum numbers in this way. And because of these Casimirs, I have two things that happens. Well, one is that I impose the simplicity constraints. So I impose the fact that I have seen this thing that boosts and rotations should be proportional one another, and this restrict in the space of all possible representations, restrict us to take only those that are respecting this constraint, and these representations are called gamma simple. But even more, because of the relationship between these Casimirs, I have also to impose that my j is equal to k. So this means, remember what I said before, when I made this decomposition of my Hilbert space, I said that I decompose in a base in which I use SU2 representations, and I take only representations not for every possible j, but only for j's that goes from k to infinity. So taking j equal to k means that I'm taking the lowest possible value of the spin, okay? So here I'm making my representation of SL2C to sit on the lowest possible value. And I can define a map that is that I call J and is labeled by gamma. And what this map does is exactly to connect representations of SU2 and map them into representations of SL2C, where, as I said, when I work with these unitary reducible representations, what I have is, concretely, the kind of object I have is like a block diagonal matrix in which in each block I have a representations of SU2. And in fact, it's double. So for each representation of SU2, I have twice a block with the same representations in the Lorentz case. So you see that, so I have constructed this Y map starting from the property of the proportionality between boosts and relations and rotations. And what this map does is exactly what we want, in the sense that it takes states that are SU2 states, the states that we have defined before, and maps them into Lorentz states, SL2C states. So now we know how our old states sits into the new one in this larger space that we have constructed. So the simplicity constraints is what does this job. Yes, question. Just one more thing, because the simplicity constraint is a classical thing, and what is happening here, it's something quantum. So you see that the simplicity constraints needs to be imposed, we said, weakly on the image of this map That means that the simplicity constraints is verified elements by elements in my big matrix. So each matrix element satisfies the simplicity constraint, but is not somehow implemented globally. So this is what the expression that you see here is telling. Yes, so the question.
So I always get very puzzled with the SL2C because for the SU2, I know that in order to get like the Hilbert spaces, you need like your inner product, your measure, and you use the fact that the SU2 is compact, and then you have your hard measure. But in this case, in SL2C, I always don't know what is done, so it's not compact.
No, it's not compact.
But that doesn't make any problem with the Hilbert space? Sorry?
Yeah, so I mean, if you do things on the real line, this is also non-compact. Yeah.
Yes.
Yeah, I mean, compactness makes things easier. And in fact, there is... Yeah, so in terms of definitions, you are safe. Then, of course, having a finite dimensional Hilbert space have advantages. And so there are situations in which you may want to go in this direction. And you can make your Hilbert space by hand finite dimensional. And this is beautiful because you discovered that this is equivalent to impose the presence of a cosmological constant. So you can think that the cosmological constant in our universe is the fact that there is a maximal horizon. And this has an implementation in the theory in the fact that you can cut the spins and have a compact Hilbert space, except that then your symmetries needs to be updated. So things get more complicated, and we don't want to, to get into these complications right now. Also, there will be lectures on the cosmological constant, but in principle, you can go in that direction. What's the question there?
Okay, so I think I lost something. I didn't follow. So why you go from SU2 to SL2C?
Well, this is
what is the motivation?
The motivation is that we started with a description of a Hilbert space in which we have a fully covariant description in terms of wave functions valued in the Lorentz group. But we want to see how this Hilbert space contains in itself the Hilbert space that we saw before. So, because very practically, as I said, when we describe a given state of the geometry, we do a measurement of this geometry, and it's just a given time for space states. So I wanted to know how these space states that in fact are what describe the boundary of this region sits into the bigger Hilbert space that is Lorentz.
Yeah, that is what I understand. But the point is like, why do we need to introduce this bigger Hilbert space rather than just stay in this SU2?
Okay, so the idea is that one possibility to see this is that we imposed the gauge fixing to start with when we were working in the previous situation. So in order to define, so the goal in the end is to define transition amplitudes that are fully covariant, and fully covariant means that they need to respect the Lorentz symmetry. and yet I needed to tell how to construct things that sit on the boundary in a compatible way with what is in the bulk. So that's the mathematical construction that allows you to do so, preserving the symmetries. And again, I wanted to go back to the original picture that I had in which I was talking about processes, right? And so the process, it's space-time itself, and it's characterized by the Lorentz symmetry. So I wanted to have something that fits with that. I wanted to preserve the symmetries. Yeah, and in the end, the goal is to go back to the Hilbert space on the boundary that I had before, but this procedure allows me to preserve covariance, and most importantly, in this process, I discover what gives me the dynamics of the theory. So these constraints, basically, is what tells me how things evolve, and it's something that I think I have finished my time, isn't it? So in the next lecture, you will see exactly how this gets together. So the first thing I will do in the next lecture is to write down the expression of the transition amplitudes.
Okay, thank you.
So I think maybe we should stop now. I know there were some more questions. Maybe you can ask them during the break. But yeah, so we'll have a 20-minute break, and we should be back here at 3:40.
Thank you.